Okay, let's get started. Today we're going to wrap up our discussion on spatial acceleration data structures, and then we're going to move on to the next part, which will be shading models. Last class, we took a look at some hierarchical spatial acceleration data structures. One example was BVH. With the BVH data structure, we start with simple bounding volumes, and then we construct hierarchies of bounding volumes that approximate smaller and smaller groups of objects. We can then use this hierarchy of bounding volumes to test intersections against large groups of objects at a time. And this can help reduce the total number of intersection tests that we perform, as well as to improve the efficiencies of the intersection tests of each intersection test. Okay. So this BVH represents an example of an object partitioning data structure where we divide up the scene in terms of groups of objects. Next, we're going to take a look at the other class of spatial acceleration data structures, which are space partitioning data structures. We saw a simple example of a space partition data structure previously, which was the uniform grids data structure. And now we're going to take a look at a hierarchical version of this kind of space partition data structure in the form of KD trees. So similar how BVH is a hierarchical version of the bounding volumes, KD trees can be thought of as a hierarchical version of the uniform grid data structure that we saw previously. Unlike the BVH data structure, where we divide up a scene in terms of groups of objects, so we partition the scene by splitting the objects into different groups. In the case of space partitioning data structures, instead of dividing up the scene in terms of groups of objects, we are instead going to partition the space in the scene into different partitions. So the idea with the KD tree is that one of the inefficiencies of the uniform grid data structure is that we divide up the scene in terms of these uniform size cells. And one of the drawbacks of this uniform partitioning is that it might not be a very it might not be very efficient. Depending on how the objects are distributed in the scene, some cells might contain large numbers of objects, while other cells will end up containing relatively few objects. So if we have a very uneven distribution of objects in a scene, with a uniform grid data structure, we might have many empty cells and then a few cells that have a very large number of objects. And this will make the intersection tests more inefficient. The idea we have with KD trees is that instead of just uniformly dividing our scene into uniform size cells, we can instead divide up the scene at different resolutions based on how many objects are contained within that part of the scene. So if a particular part of the scene contains a large number of objects, then we might allocate more cells to those parts of the scene. Whereas other parts of the scene, which are relatively empty, which does not contain very many objects, then we can allocate fewer cells to those parts of the scene. So let's take a look at how KD trees perform this adaptive subdivision. So given this scene that contains some triangles, a KD tree is first going to partition the whole scene into two halves. So let's say we might draw a partition down the middle of the scene that's going to split the space of the scene into a left half and a right half. And then we can apply this partition recursively. So for the left and the right partitions, we can partition those into two separate halves as well. For example, for the left partition, we can maybe split that up into a top partition and a bottom partition. And similarly, for the right partition, we can also split it into a top half and a bottom. And we can repeat this process. We can keep dividing the partitions into smaller and smaller partitions until each partition contains some minimum number of objects, similar to a BVH. We just apply the division recursively each time until each partition contains, let's say, 1 or 2 objects, and then we stop. Now, one of the things to note about the way that the KD tree is partitioning the scene is that some of the objects might lie in multiple partitions. So for example, when I split the right partition into a top half and the bottom half, there are 2 triangles that's going to intersect with both the top partition and the bottom partition. We mentioned before in the previous lecture that for BVHs, at a certain level of the hierarchy, every object will only belong to a single bounding volume. So we're never going to have a situation where the same object will be contained within multiple bounding volumes at the same level of the hierarchy. But in the case of KD trees, because we're dividing up the space of the scene rather than dividing the objects themselves into different groups, it's possible for an object to lie in multiple partitions at the same level of the hierarchy. So for the partition on the right, when we split it into the top half and the bottom half, 2 of the triangles are going to lie in both partitions. And that is okay in the case of a KD tree. Now, when we construct these partitions, every partition will keep track of all of the objects that intersect with that partition. So for triangles that lie in multiple partitions, then there might just be multiple partitions that contain pointers to the same object. So the same object can lie in multiple partitions. But another characteristic to make note of in the case of a KD tree is that the partitions themselves do not overlap. They're mutually exclusive. For BVH, bounding volumes can potentially overlap with each other, depending on how the objects are split up between the 2 bounding volumes. But in the KD tree, because again, we are not dividing objects, we're dividing the space itself into 2 halves, the partitions will always be mutually exclusive. So we're never going to have partitions that overlap with each other. And this can lead to some interesting characteristics for KD tree that we didn't quite have for BVH. Okay, but for the most part, when constructing the KD tree, we just apply this recursive partitioning to split the space up into smaller and smaller cells. So one of the design decisions that we have to make when constructing a KD tree is how do we decide the partitioning plane that we use to split up a cell into 2 halves? And you can use similar heuristics as those that we use for BVH. So you can use, let's say, the median heuristic or maybe even the surface area heuristic in order to try to find a good partitioning of the scene. But for the most part, the construction process will be fairly similar to a BVH. We use some heuristics to find a good partition, and then we just recursively apply that heuristic to split the partition down to smaller and smaller cells. Okay. So any questions so far about KD trees?
So to confirm, these are just it's still not showing, right?
Yeah, this partition is not uniform. In fact, one of the key characteristics of a KD tree is that the partitioning is adaptive in that it depends on the distribution of objects. If you have lots of objects in one part of the scene, then we might have many cells that's allocated to that part. And this helps to make KD trees more efficient.
And the actual cluster also is still not right? They're still not in response.
Right, yeah, the partitions themselves, like they don't have to split a cell into 2 equal halves. You can put that partitioning plane where you want, and how you pick that partitioning plane will be by using similar heuristics as what we use for BVHs. Right, so that's how we construct a KD tree. Now let's take a look at how we use a KD tree to perform intersection tests. Given the ray that traverses through the scene, we are going to, again, test for intersections between the highest partitions, and then we slowly expand down to the smaller and smaller partitions. So at the very top level of our KD tree, we have the partition that splits the scene into two halves. And then we are going to check for intersections between the ray and the two halves of this partition. In this case, the ray is going to intersect both partitions. But now for KD tree, we're going to expand the partitions based on the order in which the ray intersects them. The ray intersects with the left partition first, and then it intersects with the right partition. So we are going to first expand the left partition to check for additional intersections. When we expand the left partition, it's divided into a top half and a bottom half. So again, we're going to then test for the intersections between the ray and the two partitions in the left half of the scene. In this case, the ray only intersects with the top partition, so we have to expand the top partition to detect additional intersections. The top partition is split up into a left half, then a right half, and the ray only intersects with the right partition. So we can ignore all of the objects that's contained in the left partition, and we only have to expand the right partition. Once we expand the right partition, at this point, we have arrived at a leaf node. And so we now have to perform the more expensive intersection test against the object that's contained in that leaf node. For this particular node, we have a single triangle. So we perform an intersection test against that triangle, and we end up not detecting any intersections. So we can ignore that triangle, and then we can go back up the tree and check for additional intersections. Okay, so we're going to go all the way back up to the root node, and now we're going to check for intersections with the right half of the scene. This right partition is divided into a top partition and a bottom partition. The ray intersects with both partitions, but again, we always check for intersections in the order that the ray intersects the partitions in. Since the ray intersects with the top partition first, we are going to expand the top partition to check for additional intersections. The top partition is divided into a left half and the right half again. And the ray intersects with both partitions. But since the ray intersects with the left partition first, we're going to expand the left partition before we expand the right one. When we expand the left partition, we arrive again at the leaf node. So we are going to check for any intersections between the objects that are contained within this partition and our ray. This left partition contains two triangles. So we'll perform an intersection test against both of those triangles. And in this case, we end up detecting one intersection with this particular triangle here. And this then leads to one of the key differences between a KD tree and a BVH. In a BVH, we have to look for all intersections and then return the closest intersection, because the first intersection we find may not be the closest intersection. But in the case of a KD tree, the first intersection that we find is going to be guaranteed to be the closest intersection. And so once we have found an intersection, we can stop all intersection tests and return that intersection as the closest intersection with our ray. We don't have to perform any additional tests after that. So one of the reasons why KD trees have this nice guarantee is because the partitions themselves do not overlap. For BVH, depending on how the objects are divided between the two bounding volumes at a particular parent node, it's because the bounding volumes overlap, it's possible that the first intersection you find may not be the closest intersection. But in the case of a KD tree, because the partitions themselves are mutually exclusive, because they don't overlap, And because we always expand partitions in the order that the ray intersects them in, then when we find the first intersection, this helps to ensure that that intersection is going to be the closest intersection, that there can be no other intersections that we find later, which may be closer than the first one. So this then leads us to one of the nice characteristics of a KD tree, where as soon as we find one intersection, we can return that as the closest intersection, and we don't have to perform any additional tests. Okay, so that's one of the advantages of a KD tree, but it does have some disadvantages compared to a BVH. But one of the nice characteristics of the BVH is that we only ever test for intersections against an object at most once. So for all the objects that contained within the scene, we are only ever going to perform the more expensive test against one of those underlying objects at most once. We'll never have to test against an object multiple times. Good question. Yeah, closest just means closest intersection to the origin of the ray. So the origin of the ray starts somewhere at the top here, and the closest intersection will just be whichever intersection lies the shortest distance to the origin. Okay, right. So in the case of the BVH, we only ever have to perform an expensive intersection test against the origin or against one of the original objects in the scene at most once. We never have to test against an object multiple times. And one of the reasons for that is because every object in a BVH will only be contained within one bounding volume at a particular level of the hierarchy. So if you look at all the leaf nodes of the BVH, every object is only going to belong to one leaf node. We are never going to have the same object being contained in multiple leaf nodes. But in the case of a KD tree, because every object can intersect with multiple partitions, it means that it's possible for an object to be contained in multiple leaf nodes in our KD tree. So depending on how we expand the different branches of the KD tree, it's possible that we might have to perform multiple intersection tests against the same object multiple times. And this can end up being more expensive if the objects are very complex. So because of these different object and space partition data structures, they offer different types of advantages and disadvantages. In the case of object partition data structures, like BVHs, some of the advantages include it's a little bit easier to bound the number of nodes that we need to contain all of the objects in the scene. Another advantage of a BVH is that it's a bit easier to update the BVH when objects move around. So if objects in the scene are moving, then to update a BVH, it can be as simple as just simply adjusting the size of the bounding volume to fully contain all of the objects inside. So this kind of update can be performed fairly efficiently. If you were, on the other hand, in the case of a KD tree, it's not as easy to adjust the partitionings to account for objects that are moving around. Space partitioning data structures, on the other hand, they have a nice characteristic that, in the case of a KD tree, the first object that you detect an intersection with is guaranteed to be the closest intersection. But the drawback then is that we might have to test for intersections against the same object multiple times if you don't do some additional bookkeeping. So these are some of the trade-offs between object partition data structures and space partition data structures. But in this section, we've also taken a look at adaptive versus non-adaptive data structures. So adaptive data structures are like KD trees and BVHs, where we adjust the partitioning of the scene based on how many objects there are contained within the region of the scene. Non-adaptive data structures are things like uniform, so like the uniform grid data structure, where we simply divide up the scene into uniform size cells, regardless of how the objects are distributed. And while adaptive data structures, they generate more efficient compared to non-adaptive data structures, there are still some cases where it might make sense to use a non-adaptive data structure. With these adaptive data structures, they can be more expensive to construct. So constructing an efficient BVH might require us to, let's say, compute some expensive heuristics to find good partitionings of the objects. And this more expensive construction process means that it might be harder to update these adaptive data structures at runtime. So if you have a scene where the objects are constantly moving around and you have to update your acceleration data structure every frame, then it might be quite expensive to do this with an adaptive data structure. Whereas with a non-adaptive data structure, the update could be super simple. A uniform grid, the grid cells themselves, they don't change. If objects move around, we just have to update some pointers in terms of which cells intersect with which object. So for these non-adaptive data structures, they can be much faster to update if the scene is changing over time. But the trade-off there is that non-adaptive data structures, they tend to be more efficient when the scene is very non-uniformly distributed. So they can be more efficient in terms of performing the actual ray intersection test against these more complex non-uniform scenes. Okay. So there are lots of different choices that you can pick when it comes to spatial acceleration data structures. And as is usually the case, the particular data structure that you use is going to depend on the requirements of your application. Okay, any questions about some of these trade-offs? Okay. Well, so that's mainly everything that I wanted to discuss for these different types of spatial acceleration data structures. Now, we've presented these spatial acceleration data structures mainly in the context of trying to make ray casting more efficient, to make ray intersection tests more efficient. But these spatial acceleration data structures have applications that go well beyond ray tracing. So for example, these spatial acceleration data structures are also very commonly used for things like physics simulation. So one of the common operations that you have to perform in a physics simulator is to detect collisions between multiple objects. So if I want to simulate how objects interact with each other, one of the things we have to simulate is what happens when two objects collide with each other. And to do this, we have to detect if two objects are colliding or not. And spatial acceleration data structures can be a way to detect if there are any collisions, any intersections between objects in the scene. In addition to accelerating ray tracing, spatial acceleration data structures can also be used to make rasterization pipelines more efficient as well. So one of the operations that we have to perform in a rasterization pipeline is view-frustum culling. Whenever we place a camera in the scene, the camera is going to have some limited field of view. So this field of view determines which objects are going to be visible to the camera. And you can imagine this field of view as a frustum, as a pyramid that starts at the camera's origin and expands out into the scene. So one of the operations that we have to perform in a rasterization system is that we have to figure out which objects lie within the view frustum of our camera, which objects are within the field of view of our camera. Any object that's inside the view frustum will be an object that may be visible in the image. And anything outside the view frustum will be objects that are not going to be visible. And this is another form of an intersection test, where we have to detect intersections between the view frustum and the objects in the scene. And again, we can use spatial acceleration data structures to make this kind of intersection test more efficient. Another common application of spatial acceleration data structures is in motion planning for things like robotics. For example, let's say if you want a robot to move around a very cluttered room, then one of the common operations that you have to perform is to detect intersections between a path that the robot is going to follow and objects in the scene to make sure that there are no intersections between the robot's path and objects in the environment. And this is another form of intersection test that we can use spatial acceleration data structures to make these operations more efficient. So these spatial acceleration data structures have a lot of applications that go well beyond rendering. And depending on kind of the particular problems that you look at, these spatial acceleration structures could be a way of trying to make your algorithms more efficient, even if they might not necessarily be rendering related. Okay. Well, so that's everything that I wanted to discuss for these spatial acceleration data structures. Any final questions about this before we move on to the next topic? Okay, well, if there are no questions, then let's move on to our next topic, which will be shading models. So far we've introduced some different rendering algorithms like rasterization and ray tracing. And most of these algorithms, the primary job is to determine what is going to be visible in our image. Once we have determined what is visible in our image, the next step is to figure out what color we should assign a particular pixel in our image in order to correctly reflect what we would expect to see from that particular scene. And that is where shading models come in. So in this lecture, we're going to introduce shading models as a way of simulating light to determine what color we should ultimately assign a particular pixel in our image. And then we're going to go through some examples of different shading models that we can use to approximate how light interacts with different types of surfaces. So to start, let's take a look at what is a shading model. So given a scene, let's say here we have a scene of a bunch of different triangles. We have light being emitted by the light source that reflect off of a surface in the scene, and then that light would then be captured by our camera in order to form an image that might look like the one on the left here. Now, in order to form this image of the scene, we have to determine which objects are going to be visible at every pixel, as well as the color that we should assign that particular pixel. So in this image here, the pixels in the middle is going to observe light from the green triangle, and they might be colored in with some green color. And shading models would then allow us to determine like what shade of green, what specific green color we should assign those particular pixels in order to produce a realistic looking image. So at a very abstract level, we can think of a shading model as a way of determining what color we should assign, what color we should shade in for every surface that we observe in the scene. So a shading model is a function that takes in information about the scene, things like what the color of the light source is, what the color of the object is, and then uses that to determine the color that we should assign a particular point on the surface of an object. And this calculation is often done with the use of an illumination model. The job of the illumination model is to simulate how light is going to interact with the surface of an object and what final color we should assign a particular point on that object. We can think of an illumination model as a function that takes as input a point P in the scene. So this is some point that lie on the surface of an object in the scene. It's then also going to take some additional information that describes the scene around that point. So this might contain information like where is the light source? What's the color of the light source? How many light sources are there in the scene? As well as where are the different objects in the scene located? What are the colors of those other objects? As well as what kind of material properties are on the particular point P that we are looking at. So is the point P on the surface of a rough object or is it on a smooth object? And using all of this information, the illumination model is going to output a color, so an RGB value for the particular point P. And this would then tell us the color that we should assign that particular point and the corresponding pixel in our image. So an illumination model is going to take a scene and a point as input, and then it's going to tell us what color we should assign every point in that scene. And in practice, there are two commonly used types of illumination models: local illumination models and global illumination models. So to start, global illumination models are called global because they determine the color of a particular point based on the entire scene. In the ray tracing lecture, we mentioned that when light travels through a scene, light can bounce off of other objects. So when light bounces off of a surface, that surface itself kind of acts like a mini light source that will reflect light back to other objects in the scene. So when we are determining the color of a point, it's not enough to just look at how much light is going to reflect off of that point from the light source. We also have to determine how much light is going to be reflected off of other objects in the scene and arrive at a particular point P that we're trying to determine the color for. So global illumination models are going to try to take the entire scene into account in order to simulate the effects of, let's say, multiple bounces of light or other lighting effects in order to determine the correct value that the correct color that we should assign a particular point. Now, these global illumination models will generally give you more realistic looking images. But one of the challenges with using these global illumination models in practice is that they can be very expensive to evaluate. Let's say if you're using ray tracing to simulate global illumination, then we might have to simulate many rays, many bounces of light in order to approximate the global effects of the whole scene, how the whole scene is going to affect the color of a single point. So because of these global illumination models are often used in offline rendering applications, like for visual effects or film. And they're generally less commonly used for real-time applications, like for games. And therefore, global illumination is generally not as commonly used in rasterization pipelines, which are often used for real-time rendering applications. For real-time applications, where you have to render images very quickly, we often use a more efficient illumination model in the form of local illumination models. Local illumination models, they try to simplify the cost of evaluating these illumination models by only focusing on local effects. With local illumination models, they're going to determine the color of a point based only on local information of that particular point, and it's going to ignore everything else in the scene. So with these local illumination models, it's not going to look at other objects in the scene. It's not going to try to account for indirect illumination from other objects in the scene. It's only going to look at a single point on a single object and then use the characteristics of that object to determine the color for that particular point. So for example, with a local illumination model, the inputs might consist of, let's say, the configuration of the light source, as well as some local geometric and material properties of the particular point that we're trying to determine the color for. Oh, yeah, and then you might also take in the real camera configuration. So it's going to ignore all of the objects in the scene. It's just going to look at what's around that single point and then use that to determine the color for that point. Now, these local illumination models, because they only look at local information, they can be evaluated very efficiently. So you can implement these local illumination models in a very efficient way that can run very quickly, that can be used for real-time applications. But the drawback with these local illumination models is that because they don't take into account the global effects of other objects in the scene, the final result may not look as realistic. And these local illumination models may not be able to simulate more complex lighting effects, like caustics or refraction. But they are very fast, so they're very used commonly for things like games. So most of the rendering that you see in games might primarily use these kinds of local illumination models. So that's a high-level description of some of these different types of illumination models. Any questions about these? Okay, then next we're going to go into the details of how we actually implement these different types of illumination models. One way to think about these illumination models is that they're trying to determine the color of a particular point by quantifying how much light energy arrives at that point. So when we're trying to determine the color of a particular point, we're also trying to determine how much light is arriving at that point and how much light is going to be reflected off of that point towards our camera. So to quantify light, we're going to borrow some of the ideas from radiometry, which is the discipline of measuring electromagnetic radiation. So we can roughly kind of think of the brightness of a surface as being roughly proportional to the amount of light energy that hits that surface. In other words, we can determine the brightness, the color of a surface by, let's say, counting how many photons are going to hit that particular point. So maybe as one way of kind of visualizing how this works, we can kind of look at this ad here for the Sony Bravia TV. So we can think of the light source as emitting these particles of different colors into the scene, like all of these bouncing balls here. So these particles of light are going to be emitted into the scene, and then they're going to hit surfaces in the scene. When a particle of light hits a surface, it's going to bounce off of that surface and travel in different directions of the scene. And then it might end up hitting other surfaces and then bouncing off of those surfaces. So when we're trying to determine the color of a particular surface, this is going to depend on how much light, how many particles of photon is going to hit and reflect off of that surface. So the goal of these illumination models then is ultimately to try to quantify light and energy, how much light is going to hit and reflect off of a particular point that we're trying to determine the color for. So to quantify light energy, we're going to introduce a few terms from radiometry. So first, we have the radiant energy, which represents the total amount of light energy that arrives on the surface. And we can roughly think of this as being the number of photons that hit a given surface. So on the right, in this simple example here, we have a surface, and then we can count the total number of photons that hit the surface over some period of time. In this simple example, we have 20 hits. So we can say that roughly about 20 photons worth of energy arrived on the surface. Now, in addition to measuring the total amount of energy that arrives on the surface, another quantity that we may be interested in is the radiant flux. And this is the rate at which light energy arrives on the surface. Radiant flux is not counting the total number of hits that we observe on the surface, but it's counting the rate at which photons arrive on the surface. So in this example, we counted a total of 20 hits over the course of about 2 seconds. And so we can say that the radiant flux, the rate at which the photons arrive on the surface, is going to be roughly about 10 photons per second. Now, finally, another useful quantity is going to be the irradiance. And the irradiance refers to the rate at which photons arrive on the surface over some unit area. So for example, we might define a small patch on our surface here. And we are going to count the number of hits that we observe over that small patch in some unit over some unit of time. So in this case, let's say for this small patch of surface, we counted about 2 hits over the course of 2 seconds. So, and since the small patch has an area of epsilon squared, we can say that the irradiance, the rate at which light arrives over some unit area on our surface, will be roughly 1 over epsilon squared. So this is roughly the amount of light energy that some small unit area is going to receive on our surface per unit of time. Now, one of the reasons why we might be interested in irradiance is that irradiance is ultimately what determines the color that we should assign a given point in our image. So for light receptors, like the human eye or the camera, the color that we assign a particular pixel, the color that we assign a particular point in this image will be determined by the irradiance, how much light is going to arrive over a small area in our image. Any questions about any of these terms?
So gradients and times, like you see some gradients, but if you look at the area of the field with time, how
Right, yeah. So the irradiance represents the amount of light that arrives over an infinitesimal small area. So it's like a unit, or a small unit, like it's the amount of light energy per unit area. Yeah. So you would take the limit of epsilon to 0.
So but you can get it per point, right? Or,
Yeah, that's one way to think of it. It's just a very tiny bit of area on the surface. Okay, any other questions? Okay, so this is the high-level idea for some of these different quantities that we may be interested in. But next, let's try to assign some units to some of these different quantities. Okay. Right. So since what we care about is how much light energy arrives on the surface, arrives at a particular point, one of the things that we have to determine is how much energy is carried by a single photon of light. To determine the amount of energy that's contained within a photon, we can use the Planck-Einstein relation. So here Q represents the image that's contained by a single particle of photon. And this can be determined by a few quantities. So first, we have the Planck constant. This is some constant value that you can look up in textbook. And then multiplied by the speed of light. So the numerator here, H and C, those are constant values. And the variable that we have in this equation is the wavelength of light. So the amount of energy that a particle photon contains is going to depend on the particular wavelength of light of that photon. So here are some values that we can assign those different quantities. So H and C are constants. The Planck constant has unit of joule seconds. Speed of light, that's a speed, so it's going to be in meters per second. And the variable lambda, which corresponds to the wavelength of light, that's in meters because it's a length, and it can vary depending on the color of light. So we can have short wavelengths. So this visible light roughly falls within this range for the wavelength. So depending on the wavelength of light, we might get a different amount of energy that's stored within each photon. Now, if you multiply out all these units, what you're going to get at the end is going to be a unit of joules, which makes sense for the amount of energy that's in a particular photon. So the radiant energy is going to be given in terms of joules. And with this, we can then figure out the units for some of the other quantities that we defined in the previous slide. So in the case of radiant flux, this is the amount of energy per unit of time. So this is given by joules per second, which is going to be watts. Irradiant, on the other hand, is given by the radiant flux per unit area. So unit area is going to be given by meters squared. So the units that we can assign for irradiance is going to be watts per meter squared. So when we are implementing an illumination model, when we are trying to determine the particular color of a point, what we want to determine is going to be the irradiance. How much light is going to arrive at a particular point over some unit of time. Okay, this might be a good point to go for a little break. I guess any questions about any of this before we take a 10-minute break? Okay, if no questions, then yeah, we will take a break until 3:30. Okay, let's get started. Now we've introduced some of these different terminology for quantifying light energy. Let's take a look at how we implement some of these concepts in illumination models. Okay, but first let's take a look at how we represent different colors for these illumination models. So far, we've talked about light in terms of the amount of energy that arrives on a surface. But light can, depending on the wavelength that the photon, or depending on the wavelength of light, they can end up producing different colors. So given a particular light source, the light source might emit light of different colors. And one way that we can quantify the color of the light that's being emitted by a light source is by using the spectral power distribution of that light source. And you can think of the spectral power distribution as a histogram that tells you how much light of different wavelengths are being emitted by the light source. With these in these spectral diagrams, on the x-axis, we have the wavelength of light. And on the y-axis, we have the amount of light that's being emitted at those different wavelengths. So on the top left, we have the spectral power distribution for natural sunlight. And from the sun, what we generally observe is a fairly uniform distribution of light. So we get light being emitted at a wide range of different wavelengths. So this represents relatively neutral white light. Then on the top right, we have the spectral power distribution for incandescent light. So the light that you might see in some of the older light bulbs. And for these light sources, we see a large skew towards light of lower wavelengths. So the light that's being emitted by these incandescent light bulbs tend to be redder. They tend to appear as a warmer color compared to the sunlight. Then in the first spectral power distribution on the second row, we have the distribution for fluorescent light. And when you look at fluorescent light, what you generally see is that the distribution is very uneven. Most of the light is being emitted at very specific wavelengths. And it's also one of the reasons why people would complain that fluorescent light kind of gives a very artificial, unnatural glow. And part of the reason is due to this very uneven distribution of the wavelengths of light that's being emitted by those light sources. Oh, and there's power distributions of some other types of lights as well. So if you want to accurately model the color of the light source, we'll have to model the full distribution of light that's being emitted at all of these different wavelengths. And that can very quickly become extremely expensive. But luckily for us, for the purposes of computer graphics, we can take a little sheet to try to make these lighting calculations more efficient. On the bottom left, okay. Okay, we don't have quite the diagram here, but so to try to make these lighting calculations more efficient, we can take advantage of some of the characteristics of the human visual system. As we mentioned in the previous lecture, the human eye contains receptors that are sensitive to specific wavelengths of light. And in particular, for most people, our eyes have receptors that are sensitive to 3 different wavelengths of light that roughly corresponds to red, green, and blue. Which means that if we want to simulate most of the light most of the different colors that the human eye can perceive, we, for the most part, just have to determine how much red, green, and blue light is being emitted by the light source. And by combining different amounts of red, green, and blue light, we can more or less simulate most of the colors that the human eye can see. And this can then greatly simplify our lighting calculations and our illumination models. Instead of trying to model the full distribution of light of all different wavelengths, we only have to model how much light is being emitted and reflected by the different objects in the scene. Sorry, how much red, green, and blue light is being emitted and reflected by objects in the scene. And that would give us a reasonable approximation of the colors that humans would be able to see. So for the remainder of the lecture, whenever we talk about color, whenever we talk about, we are going to assume that we'll be using the RGB representation. So every color will be represented by a vector of 3 numbers, corresponding to the amount of red, green, and blue light that's being emitted or reflected by an object. Okay, so now that we have that out of the way, let's take a look at how we can implement a simple kind of illumination model. So the first illumination model that we're going to look at is going to try to capture this intuition that we all have when we are looking at the surface of an object. Some parts of the object will look darker, and then some parts of those objects will look brighter, depending on the configuration of that surface with respect to the light source. In this image here, we have this wall that contains a bunch of different facets that face different directions. And intuitively, when we look at an image like this, we can more or less understand that every point on this wall probably have the same underlying color. But when we see the wall, we see the different patches on this wall have different brightness depending on their orientation. So I've highlighted 2 specific patches on this wall. One patch is facing towards the light, and it ends up appearing with a bright color, whilst the adjacent patch is facing away from the light, and it ends up appearing darker. So the intuition that this illumination model is going to try to cover is that surfaces that are facing towards the light should be brighter, and surfaces that face away from the light should appear darker. And we can use some of the concepts from radiometry to explain what the cause of this intuition is. So the brightness of a surface can be roughly determined by the amount of radiant flux that arrives on the surface. So here phi represents the radiant flux, which is the amount of energy that arrives over the surface area of a particular surface over some unit of time. And the total amount of radiant flux that arrives on the surface of an object is given by the irradiance E. So how much light is being emitted per unit of time and per unit area, multiplied by the area of that surface. So if you have a larger surface, then there's going to be a larger amount of light that's going to be captured by the whole surface. And similarly, if we have a smaller surface, the total amount of light that's going to hit that surface is going to be lower as well. Okay, so the total radiant flux that arrives over a whole surface is going to be determined by the irradiance multiplied by the area of the surface. Okay, now let's say we take a surface and then we tilt it away from the light source. In this example, I've taken a surface with some area A, and I've rotated it away from the light by some angle theta. Now, when we rotate the surface away from the light, the cross-sectional area of the surface that intersects with the light has now been reduced. The original surface has an area of A, but when we rotate it away from the light source by some angle theta, the cross-sectional area, so the effective area that's going to intersect with the light that's traveling in that direction, is going to be reduced down to some smaller area that we're going to refer to as A prime. So the total amount of light that arrives on the surface is not determined by the area of the surface itself, but by the cross-sectional area that intersects with the light beam. So now when we rotate the surface, the total radiant flux that arrives on the surface is going to be given by the irradiance, which is constant, that's determined by the light source, multiplied by A prime, which is the cross-sectional area. And we can express A prime in terms of the original area of our surface as well. So A prime in this case will be given by A multiplied by cosine theta. So the amount that we rotate the surface away from the light. So the larger theta is going to be, the smaller the cross-sectional area is, and the smaller the radiant flux is going to arrive over the surface of our object. So what the radiant flux tells us then is that surfaces that are facing towards the light is going to receive more energy, and then surfaces that face away from the light is going to receive less energy. And the amount that the energy decreases is going to be determined by some cosine relationship between the angle of the surface and the direction that the light is traveling. Okay, any questions about this example before we go into the math? Now, this behavior can be roughly modeled by a very simple illumination model called the Lambertian diffuse model. And the Lambertian diffuse model is going to try to model this phenomenon where surfaces that are pointed towards the light will be brighter than surfaces that are pointing away from the light. And this is a super simple lighting model that can be implemented by just that short line of code that you see on the screen there. So let's analyze this lighting model. So the color of a particular point on our surface is going to be given by this simple equation here. The key component of this lighting model is going to be this dot product. In the Lambertian model, we compute a dot product between a normal vector and a light vector. The normal vector represents the direction that the surface is facing. So the normal vector is going to be a vector that's orthogonal to the surface of our object. Then we also have a light vector L. The light vector is going to be a vector that points from the point that we are trying to determine the color for, and then it's going to be pointing towards the direction of the light source. So this is not the direction that the light is traveling in. It's the opposite direction that the light is traveling in. So it's the direction from the point to the light source. It's not the direction from the light source to the point. So that's a little bit of implementation detail that you need to watch out for. Now, given the light vector and the normal vector, the Lambertian model is going to compute a dot product between these two vectors. And this dot product is going... Now, when we compute a dot product between two normal vectors, two unit length vectors, this is going to give us the cosine of the angle between the two vectors. So when we compute a dot product between the normal vector and the light vector, this would then give us the cosine of the angle between the two vectors. And this is going to implement kind of a cosine law that we saw in the previous slide, where we can use the cosine to determine whether or not the surface is pointing towards the light or away from the light. And we can use this cosine to determine how much light energy is going to arrive at a particular point. Okay, so let's take a look at how this model behaves under different configurations of the light source. Let's say the light source let's say the surface is pointing directly towards the light source. So here the normal vector is exactly aligned with the light vector. So since the surface is pointing exactly towards the light source, the dot product between the normal vector and the light vector is going to have a value of 1. It's going to have a maximum value that represents the most amount of light energy that's going to arrive on the surface of our object. Okay. So this is going to give us the brightest color for our light source. Oh, thanks. Okay, but now as we move the light source away from the normal, so as we rotate the surface to point away from the light source, the angle between the light vector and the normal vector is going to increase. And as the angle between the two vectors increases, the cosine of the angle is going to decrease. So it's going to give us some value that's less than 1. And this represents a smaller amount of light that's going to arrive at a particular point as we face away from the light source. Now, as we keep moving the light source further and further away from the normal vector, at some point, the light vector is going to be orthogonal to the normal vector. This would then give us a dot product of 1, so a dot product of 0. This corresponds to the case where the cross-sectional area between the surface and the light source will be 0, because the surface is facing exactly away from the light source. So exactly orthogonal to the direction of the light source. So the surface is not going to receive any energy from the light source, and it's going to end up with a very dark color. Okay, but now something strange happens as we keep moving the light source further and further away from the normal vector. If we keep moving the light source, at some point the light source is going to go below our surface, which means that the angle between the light vector and the normal vector will now be greater than 90 degrees. And the cosine of that angle is going to be less than 0. And this then leads to a behavior that doesn't necessarily make sense anymore. If we have a negative value in the dot product, this ends up representing negative illumination. This is kind of like saying that if we rotate the light source far enough away from the normal vector, not only is the surface not receiving any energy from the light, but the light source is somehow sucking energy away from the point, from the surface. And this doesn't really happen in the real world. Like, we don't expect to see some point with like negative illumination just because the light source is below a surface. So this is an artifact of the cosine model. And so the Lambertian model tries to fix this artifact by adding a clamp to the dot product. So we're just going to add a max that's going to clamp all negative values to 0, which means that whenever we have a light source that's under the surface is just going to be completely black. It's not going to receive any energy from the light source. Okay. So with this dot product, we can then have a simple mathematical model that captures the behavior that we saw in some of the previous slides, where surfaces that point towards the light will be bright, and then surfaces that point away from the light will be dark. So, any questions about that? So this dot product is the core component of the Lambertian model and allows us to roughly approximate how much light is going to arrive on a particular point on our surface. And then there are a couple of other constants here. So first, we're going to take the cosine, we're going to take the dot product, and we're going to multiply it by some light intensity value. The light intensity here represents a color, the color of our light source. So this is going to be some 3D vector that specifies the amount of red, green, and blue light that's being emitted by our light source. Now, besides the light intensity, we're also going to modulate the color of our light with an additional term called the albedo. And this albedo value represents the underlying base color of our surface. So it's a little history of where this term albedo comes from. The term albedo comes from the magnum opus, which is the alchemical process of creating a philosopher's stone. So let's say if you want to create yourself a philosopher's stone, you typically have to go through some different stages. So the first stage is called nigredo, which means blackening. So in alchemy, if you try to make a philosopher's stone, in the first step, your base materials might turn black. The second stage is called albedo, which represents whitening. So at this stage, the material turns white. And then the final stage of the process is called rubedo, which means reddening. So at that point, the material turns red and you hopefully have yourself a philosopher's stone. So the albedo term in our illumination model comes from this second stage here, which represents whitening. And here, albedo represents the amount of light that's being reflected by the surface. So a surface with a high albedo value will appear white because it's going to reflect light uniformly in all directions. It's going to reflect light of all different colors roughly uniformly. So this will correspond to an object that's going to be white if you illuminate it with uniform light. Whereas an object with a low albedo value will end up appearing very dark, something close to black. This corresponds to a surface that's going to absorb most of the light that hits that surface. So with this albedo, we can specify the underlying color of the surface that we are trying to color in, that we are trying to shade under uniform illumination. And with this simple Lambertian model, we can already create a pretty reasonable looking image of an object. Here we have a rendering of the Stanford bunny that's being illuminated using the simple Lambertian model. And we can already see a pretty reasonable result. Parts of the bunny that's facing towards the light source, in this case, the light source is somewhere on the upper right-hand side. Surfaces that are facing towards the light will be bright, and surfaces that start to face away from the light will appear darker and darker. So we can already get a pretty reasonable 3D effect from this very simple lighting. Right. So this is a simple Lambertian model. It's quite the simplest version of a lighting model that we can implement. And it can already give us some pretty reasonable results. Any questions about this Lambertian model?
But the atmosphere, is it calculated like for reflection and interpolation or?
Oh, right, yeah. So one thing we haven't discussed is what are the actual points that you apply the lighting model to. And we will talk about some of the different methods that we can use at the end of the lecture. But yes, so one method is to apply the lighting model to every vertex and then interpolate the color. The other way that's more commonly used is that you apply this lighting model to every pixel that you're trying to color in. So you use this lighting model to determine the color of every pixel. Yeah. Any questions or other questions about this? Right. Now, before we take a look at some more sophisticated lighting models, let's discuss a little bit about some of the different types of lighting sources that we often use in rendering. So in the real world, we have lots of different light sources. We have light from the sun, we have light from artificial light sources as well. And if we want to create realistic images of a scene, we need to have different models of light sources that we can use for also these different types of lights. So when we are rendering a scene, we will often use a combination of different light sources. So one common type of light source is called ambient light. And this is a very strange type of light source that doesn't really exist in the real world. But it's kind of trick, a quick hack to try to approximate global illumination. So an ambient light represents a light source that emits uniform light in all directions, from every single point and in all directions. So you can think of the ambient light as kind of like a uniform glow, a uniform glow that permeates your whole scene. It just emits light from every single point in uniformly in all directions. So the way that you implement this ambient light source is that it might just be a constant light color that you apply to every single point, regardless of the position or the orientation of that point. So this kind of light source doesn't really exist in the real world. But the reason why ambient light is used very commonly in practice is that it's a very cheap way of approximating global illumination. You can think of the ambient light as the color that you get once light has bounced an infinite number of times in the scene and has mixed together, has mixed uniformly. So for real-time rendering systems where we may not necessarily be able to implement global illumination, this ambient light is a kind of quick hack that we can use to roughly approximate the effects of global illumination. Another common light source is a directional light. And this corresponds to a light source that's going to be that's infinitely far away, something like the sun. When you have a very far away light source that's emitting light into a scene, then all the light rays that are being emitted into the scene are going to travel in exactly the same direction. So with directional light, regardless of the position of a point in the scene, light is always going to hit that point in the same direction. Another commonly used type of light is going to be a point light source. This will be something kind of like a light bulb, where you have a light source located at a specific position in space, and then it's going to emit light uniformly in all directions. In the case of the point light source, the direction that the light hits a particular point is going to be dependent on the relative position of that point with respect to the light source. So let's say if you want to apply the Lambert model to a point light source, the light vector is going to change depending on the position of the point with respect to that light. In contrast, if we apply the Lambert model to a directional light, the light vector is going to be constant. It's going to be some constant vector regardless of the position of my point. Now, another common type of light source is going to be a spotlight. This is, you can think of the spotlight as a special case of a point light, where the light source is only going to emit light along specific directions. So if a point is within this range of directions of the light source, then it's going to receive light from the light source. If the point is outside of this range for the light source, then it's not going to receive any light. And in practice, you'll use a mixture of these different light sources in a scene in order to kind of create the particular lighting conditions that you want for your scene. Any questions about these different types of lights? Right, then let's take a look at how we implement some of these different types of lights. And we're going to focus specifically on point light sources. Point lights are also sometimes called isotropic point lights because they emit light uniformly in all directions. So if we want to apply an illumination model to a point light source, one of the things that we are going to have to determine is how much light energy is going to arrive at a particular point in our scene. So for point lights, because all of the light is being emitted at a specific point, the amount of energy that hits an object in the scene is going to be dependent on the distance of that object from that point light source. So to determine how much energy is going to arrive at a particular point P, we can determine that. We can determine the radiant flux that arrives at a point P. Wait, sorry, no, not quite. We can determine the irradiance that arrive at a particular point P by looking at the radiant flux of the point light. Okay, so as a reminder, the radiant flux represents the total amount of energy that's being emitted by the light source over some unit of time. So we can think of the light or point light source as it's going to emit light starting at a particular point, and then all that light is going to travel uniformly in all directions into the scene. So we can think of the light that's being emitted by the light source as lying on the surface of the sphere, centered around the point light source. So the radiant flux that's being emitted by this light over some period of time is going to be fully contained on the surface of the sphere. And then it's going to expand out into the scene. What this means then is that if you look at 2 points at different distances from the light source, R1 and R2, and we can think of a sphere that's that lies on that contains those points, the total amount of radiant flux that lies along those 2 spheres has to be exactly the same. So since light is being emitted from the source and expanding to the scene, regardless of how far we are from the scene, the total amount of light that lies along the sphere that's emanating from the point is going to contain the same amount of energy, the same radiant flux. And this then gives us a way of determining the irradiance at different distances from the point light source. So we know that the flux of the light sphere of different radiuses is the same. So phi is going to be the same regardless of how far we are from the light source. Which means that phi is the radiant flux is going to be determined by the irradiance at a particular distance from the light source, multiplied by the surface area of the sphere that has that particular radius, that particular distance from the light source. So the total flux at some distance, R1 from the light, can be given by the irradiance E1 multiplied by 4 pi r squared, which is the surface area of a sphere with radius R1. And this is going to be equal to the flux on a sphere with a different radius R2. So if we have another point that's some distance R2 away from the light source, then the flux will be given by the irradiance at that distance E2 multiplied by 4 pi R2 squared. Okay. So we can do a little bit of algebra, and what we want to determine is going to be the irradiance E1 and E2. That's going to tell us how much light energy is going to arrive at a particular point at that distance from the light source. Yep. So if we do a little bit of algebra, what we are going to see is that the relationship between E2 and E1 follows an inverse square law. So the ratio between E2 and E1 is going to be equal to the ratio between R1 and R2 squared. Which means that as we move away from the light source, the irradiance of the light source is going to drop off by the square of the distance. So what this means is that the further away from the light source, the dimmer the light source is going to appear, which I think generally makes sense. So if you want to apply a lighting model to a point light source, depending on how far an object is from the light, we would decrease the irradiance of the light source by the square of the distance. Okay. Any questions about this?
Was the radiant flux the same, or not also drop off?
So the radiant flux here is phi, and that's constant regardless of how far you are away from the light source. Yep. So the radiant flux you can just think of as like the surface area of the sphere that expands out from the light source. Oh sorry, no, I'm sorry. So the radiant flux is a total energy along the surface of the sphere. And as you make the sphere larger and larger, you're just stretching the same amount of energy across a larger and larger area. So the total amount of energy is the same, but it's now just being spread over a larger area. Right. So the radiant flux is constant, it's the irradiance that drops. Any other questions about this? Okay. So those are some of the different common light sources that we'll use. Now let's go back to different lighting models. The Lambert model that we've looked at so far, it's a model for simulating how light interacts with a specific type of surface. These surfaces are sometimes referred to as Lambert surfaces or diffuse surfaces. And these surfaces represent very rough objects. So think of something like concrete. For when light hits these very rough surfaces, they reflect off roughly uniformly in all directions. So when you have a very rough surface, all of the light is going to reflect off in all different directions roughly uniformly. And the Lambertian model is kind of an approximation of what happens with these rough surfaces. And as a result, the Lambertian model is a reasonable model for rendering rough surfaces. But it's not very good at approximating the appearance of a smooth, glossy surface. So if you look at objects in the real world, they're generally not perfectly rough. So for example, for some objects, they might have very smooth reflective surfaces. And for these smooth objects, they reflect light in a different way compared to diffuse surfaces. For smooth surfaces, they will typically reflect light only along very specific directions. And you can think of this as kind of like a mirror reflection, where light hits a surface, and then it's going to be reflected back in a specific direction. And these types of mirror-like reflections are called specular reflections. Light comes in, and then instead of scattering in lots of different directions, they just reflect back out along a specific direction. And if you look at the different types of surfaces that we see in the real world, they're generally not perfectly rough and they're not perfectly smooth. They often fall within some range in between these two extremes. So instead of perfectly rough surfaces or perfectly mirror-like surfaces, most of the objects that we see in the real world are some mixture of the two. They're not perfectly rough and they're not perfectly smooth. And we refer to these surfaces that fall in between these two extremes as glossy surfaces. So these glossy surfaces, they're going to reflect light back in different directions. But then most of the light is going to be concentrated back in some specific directions. So with these glossy surfaces, you can think of this as, because the surface has some roughness to it, when light hits that surface, some of the light is going to be reflected back along a very specific direction, like a mirror reflection. But some of the other light is going to be reflected back in other directions because of the rough patches on the surface. Our Lambertian model is really only able to model reflections on these very rough surfaces on one end of the spectrum. But if we want to render different types of surfaces, we have to develop more sophisticated lighting models that allow us to approximate these glossy reflections. And that's what we're going. Okay, so next we're going to take a look at some more sophisticated lighting models that allow us to approximate reflections on these glossy surfaces. One simple model that we can use for modeling these. Oh, right. So first, we're going to take a look at how we model specular mirror-like reflections on smooth surfaces first. One simple model that we can use to model mirror-like specular reflections is the Phong specular model. So the Phong specular model is somewhat similar to the Lambertian model. It also relies on dot product to determine how much light is going to reflect off of the surface in a certain direction. But this dot product is going to be computed using different vectors. So the way to interpret the Phong specular model is that we are going to compute the intensity of light that's reflected off of a certain direction by using a dot product between two vectors, R and V. Okay, so to define these two vectors, so let's say we have a surface with some normal vector n, and then we're going to have some light vector along some direction L. Next, we are going to define a view vector. The view vector represents the direction from the point to the camera. So similar to the light vector, the view vector is not the direction that the camera is looking at. It's the opposite direction of the camera's view direction. So it's pointing from the point to the camera, not from the camera to the point. Now, in the Phong vector, to implement the Phong model, we're going to define a reflection vector, which is the reflection of the light vector along the normal vector. So the reflection vector is given. Let's say light is going to travel from the light source to the point N along the direction of negative L. So the light vector is, so the negative of the light vector give us the direction that light is going to be traveling in from the light source. And if we reflect our vector along the normal vector, this is going to give us the reflection vector R. And the reflection vector represents the direction the light is going to be reflected off in if we have a perfectly smooth mirror-like surface. If you have a perfect mirror surface, light that travels along the direction negative L is going to be perfectly reflected along that specific direction R. Now, the Phong model is then going to compute a dot product between the reflection vector and the view vector of the camera. So to illustrate what the behavior of this model is, let's go through some different configurations of the scene. If the camera vector is aligned with the reflection vector, then this is going to be the scenario where we get a dot product of 1, which represents a maximum intensity. If we have a perfect mirror surface, all the light that hits a particular point P is going to be reflected along the reflection vector R. So this is the direction that we're going to expect to see most of the reflected light. All the reflected light will be concentrated in that particular direction. But now as we move away from the reflection vector R, the angle between the V and the R vectors are going to increase. And so the dot product is going to decrease and we get a lower intensity reflection. So since most of the reflection is concentrated along the reflection vector R, if we move away from the reflection vector, then we are going to see a lower intensity. Then we're going to see less and less light being reflected along that direction. Now, similar to the Lambertian model, if we move the camera very far away from the reflection vector, at some point, the angle between the R and V vectors are going to be greater than 90 degrees. So we are going to again get negative values from the dot product. And therefore, we have to introduce this clamp to clamp all negative values to 0 so that we don't end up getting negative intensity from the lighting model. Okay. All right, so that's similar to the Lambert model. Okay. But now for the fog model, because we never have perfectly smooth surfaces, we need to model how light is going to be reflected off of surfaces with different roughness. And the roughness of a surface is going to be modeled by this shininess coefficient. For the most part, you can just think of the shininess coefficient as a magic number that tells you how smooth a surface is. If the shininess value is high, then we have a very smooth surface where most of the reflection is going to be concentrated along the reflection vector R. So the higher the shininess value, the more mirror-like the surface is going to behave. If you have a very low shininess value, then we are going to get more diffuse reflection, where more and more of the light is going to be reflected off in directions other than the reflection vector R. So as the shininess coefficient decreases, the reflection lobe becomes wider and wider, which simulates more diffuse reflection on rougher surfaces. So in practice, the shininess value is a coefficient that you have then authors might have to tune by hand in order to capture the reflection that they want to see on a particular surface. You can also try to estimate these values by like taking lots of measurements of a real surface as well. But for the most part, this shininess coefficient's just kind of a magic number that you have to tune and figure out, that you have to tune to get the particular appearance that you want. Okay, so this might be a good point to stop for this lecture. Any final questions before we wrap up for today? Oh, yeah. Not quite so. If the camera is aligned with the light source, depending on the shininess value, you might still see some reflected light in that extreme direction. You might not see a lot, but if the shininess value is low, then you might still see some light in some of those, yeah, along the light directions. Any other questions? A question in the chat about if the little caret represents an exponent. Right, yeah. So the shininess value is we take a dot product and we take it to the power of the shininess value. Yeah, so that's an exponent. Okay, if there are no other questions, then we'll wrap up for today.